Hello everybody, welcome to this MOOCs online video course Theory of Yarn Structure. Today we will continue with module 8 Tensile Mechanics of Yarns. If we recapitulate what we did in the last class, we were trying to derive a generalized theory on tensile behavior of staple fiber yarns. So, we started with basic concept of stress and strain in yarn, then what is the stress strain diagram, then we developed a theory of tensile mechanics of yarns according to helical model. Then we introduced some simplified assumptions and we derived the expression for Gagoff's theory. Now, Gagoff's theory states that the coefficient of fiber stress utilization in yarn is constant irrespective of yarn axial strain is low or high. This gives a problem because it does not correspond to reality. Experimentally, it was observed that this coefficient changes as the yarn axial strain is changing. However, Gagoff thought it to be a constant. What was the reason? Is it possible to derive some newer expression so that it will correspond better with the experiment and reality? So, we were trying to do that. So, we were basically trying to partially generalize the helical model. What is the meaning of partial generalization of helical model? In helical model, it was assumed that the angle of fibers is same, deterministic. However, in real yarn the angles are random, stochastic. So, we are just changing this from deterministic to stochastic angle of fiber orientation. The idea based on which we were working, we showed you. So, initially it was a planar strip of fibers. So, it is some sort of this. So, this planar strip of fiber will be rolled to form a cylindrical structure and it forms a cylindrical structure. In this planar strip of fibers, the angle theta is different for different fibers. However, there is a tendency that the mode of the fibers, mode direction, the preferential direction is not y axis, but it is inclined at an angle beta from the y axis, right. Then we used what we learned in the theory of fiber orientation and we were discussing about the how the fiber orientation distribution can be considered. Now, because of doing this, there are certain changes occurring from our earlier expressions. Let us talk about that. Now, in the earlier, if you remember well, then you have probably seen that this expression sin square beta. Now, this expression is no more valid in this theme. Why? Because earlier the angle was beta, now the angle is theta, and beta is the modal angle. So this beta is now changed to theta. So what expression will be valid here? Sin square theta, right. So that is why we wrote this expression, cos square theta minus eta sin square theta. Okay. We need to find out two limits of this angle theta. One limit is very clear, when theta is equal to 0, epsilon f is equal to epsilon y. So there must be another limit at which epsilon f will be 0. So that angle is theta subscript u, upper limit. So that angle is this. This obviously generates a question. The question is, what will happen if this angle theta is greater than this angle, but less than pi by 2, less than equal to pi by 2. For that, so if you use this, you see that when theta is equal to pi by 2, so this becomes 0, this becomes some value 1, so it becomes negative. Epsilon f is negative. What does this mean? Physically, fibers is not elongated, fibers is compressed. Such phenomenon is very difficult to imagine in practice. Even if such phenomenon is present, number of fibers experiencing such phenomena will be too low, and for such situation the yarn force can be considered to be 0 for those fibers. So we will consider the angle lower limit 0 and upper limit theta subscript u. Okay, right. Now we will develop the force in yarn. So in this partially generalized model, what will be the function for f subscript y? This we would like to develop. Now, what is the force in fiber? That is your this force. So suppose this is your yarn axis, this is your fiber axis. This force is this force. What will be the force along the yarn axis? Let us say this force is indicated by F subscript A. So this F subscript A must be equal to cos theta, right. Now, so theta is lying from 0. So, theta will lie from 0 to theta u. Okay. So, now there will be many fibers in that differential layer we considered. So, and all fibers will have different value of theta. So, the mean component of force per one fiber to the axial direction of yarn is F this. This must be from the definition of mean F subscript A u star theta d theta, the angle from 0 to theta u. Now, what is F subscript A? F subscript A is F subscript F into cos theta. So, we write 0 to theta u into cos theta into u star theta d theta. Okay. Now, what is u star theta? U star theta was equal to cos theta u theta by kn. So, if we substitute this, what will be the expression? 0 to theta u cos theta u theta kn d theta. So, this cos theta into this cos theta will be cos square theta. So, let us write down after rearrangement 0 to theta u cos square theta u theta by kn d theta. Right. If we substitute now for stress, so stress is force per unit area and density component will come because of engineering, because of the relation between engineering stress and specific stress. So, if we substitute, what we get? Sigma f epsilon f s rho kn, it is a constant term, cos square theta u theta d theta 0 to theta of u, right. So, what we observe is this function. Now, this is a constant, so it can come out of integration. d theta, right. Now, this force is experienced by the whole differential layer. So, what is the total force experienced by the whole differential layer? Total force experienced by the whole differential layer is d small force F y. So, that is equal to this force into dn, because dn is the number of fiber portions. Right. Now, what is dn? 2 pi r into dr into mu by a star, and a star is S by cos theta. So, let us write down this expression d f y will be dn. So, basically 2 pi r mu dr by a star into S rho by k n integration 0 to theta u E f cos square theta u theta d theta. Right. What is Kn? Kn is S by a star. So, this S star, S and Kn, they are cancel out. As a result, what we find dFy is this. This is the force in the only in the differential layer. So, what is the complete axial force in complete yarn? So, total force, axial force in the entire yarn is integration of this from r is equal to 0 to r is equal to d by 2. So, that force is this integration d of y r is equal to 0, r is equal to d by 2. Okay. So, what we obtain is two pi r mu into rho dr 0 theta u f cos square theta u theta d theta. Let us write it in a more correct form. So, this 2 pi mu rho will be out of this integration, 2 pi mu into rho integration r is equal to 0 to r is equal to d by 2 integration 0 to theta u Ef cos square theta u theta d theta, then r dr. Is that correct form? Yes. 2 pi mu into rho, there are two integrations because of two variables, one is r, second is theta, and this r and theta are probably not related. So, r is equal to 0 to d by 2, this integration into r dr. Okay. Right. Now, what we have to do? We have to change this r in terms of angle beta. So, how we can do this? So, it is now simply rearrangement. Say r is equal to 2 pi r z by 2 pi z. You remember similar thing we did when we derived Gegoff's theory earlier. So, if we assume this, beta 2 pi z d tangent beta 2 pi d z d by 2 beta by tangent of beta d. If we substitute, then you derive it right, then you finally substitute all, then what expression you will obtain, let me write it once. This as a function of y will be 2 pi mu into rho, that will remain there, into d by 2 tan beta square, then into then the 0 to beta d, 0 to theta u Ef cos square theta u theta d theta, then you will find sin beta by cos cube beta d beta. This form you will obtain, relatively long, 2 pi mu into rho d by 2 tan beta d square 0 to beta d sigma f epsilon f cos square theta u theta d theta sin beta by cos cube beta d beta, right. Now, you substitute one more relation, that is your d square is equal to 4 t by pi mu rho. If you substitute that, then what you will see, you will obtain this is equal to 2 by tan square beta d, it is constant, t is constant, beta d is constant, 2 is constant, 0 to beta d theta u f cos square theta u theta d theta multiplied by sin beta cos cube beta d beta okay. So, this is the expression for force. What will be the expression for stress? So, now for stress, this must be y, not f. For stress, is by capital D. So, this is the definition. So, this from this expression, this T will go out. So, we will have 2 by tan square beta d 0 to beta d 0 to theta u f cos square theta u theta d theta is the one integration, then sin beta by cos cube beta is the second integration. Okay. As I said you earlier, we always work for 3 equations. One is force, second is stress, third is utilization. So, what will be utilization? This divided by this. This is the definition of stress utilization, right. So, what we will have 2 by ui tan square beta d 0 to beta d 0 to theta u into d beta, right. So, this will be the expression for utilization. Now, we would like to discuss about the calculation part. So, these 3 equations we have finally derived based on partial generalization of helical model. So, this was the first expression, this was the second expression, and this was the third expression. Now, the question is how to calculate based on these 3 equations, how to calculate force, stress and coefficient. So, that is what we would like to discuss now. So, the calculation part, we are interested in finding out the calculation part. Three functions we need to find it out. One is this value, second is this value, third is this value. What are known? Given fiber stress strain must be given. This must be known to you. Then you must know some parameters: yarn twist, fiber density, yarn diameter, packing density, contraction ratio. C is measure of anisotropy that we discussed in theory of fiber orientation. So, these parameters you must know, plus you should also know 3 other quantities. One is this quantity, second you must know this, third you must know kappa tangent of beta d pi dz. So, if you know these 3 quantities, then you will be able to find out these 3 functions. How? Because we know these functions now, say f y t 2 by tan square beta d 0 to beta d theta u f cos square theta u theta d theta sin beta by cos cube beta d beta. This was one function for force acting on yarn. Second is stress developed in yarn 2 by tan square beta d 0 beta d theta u f cos square theta u theta d theta sin beta cos cube beta d beta. Right, and the last expression was related to coefficient of stress utilization. So, 2 by y tan square beta d beta d 0 to theta u sin beta by cos cube beta d beta. So, these equations are very, very important. So, once again I repeat how to calculate these 3. So, our aim is to find out these 3 values. So, there should be some given parameters. What should be given? Fiber stress strain relation you must know. Also you must know yarn twist, yarn diameter, yarn packing density, yarn contraction ratio, measure of anisotropy and fiber density. Also you must know the relation between fiber strain and yarn strain. You should be able to calculate fiber strain, theta u and kappa tangent beta d pi dz. So, if these values are given, then by using these 3 equations you should be able to calculate these 3 functions, right. So, now we will talk about one theoretical example. We will follow exactly the way we described for calculation. Let us consider for this particular example the fiber stress strain relation is linear. The moment we assume fiber stress strain relation is linear, automatically this phi is independent of yarn strain, that is phi. So, why in Gegoff's theory we obtain constant value for tensile force utilization in yarn? The reason is very simple, because of the assumption of fiber stress strain relation is linear. Had it not been considered, we could have got different values for coefficient of utilization for different values of yarn strain, but that is basically giving it. All right. So, for this theoretical example we consider fiber stress strain is linear. As a result, consequently we obtained this is independent of strain. Nevertheless, there will be another influence on coefficient of utilization. What will be that influence? That influence will come from fiber orientation. So, the level of utilization in yarn will vary as the angular distribution of fibers in yarn will vary. So, it is not so that for all yarns it will be same. the yarns having different degrees of fiber orientation anisotropy, their value of phi will be different. So, that means the dominant influence now will come from C. Measure of anisotropy. This C will now be the key factor which will make it different from Gegoff's theory. Let us consider first C tends to infinity. So, if C tends to infinity, then u theta 1 by pi C by plus 1 by pi you can find out in that case this one will be tan square beta d. So, that means in that case you will find out this will be equal to Gegoff's theory. So, we will obtain Gegoff's equation. Equal to cos square beta d if this 0, right, then it will be Gegoff's equation. Now, what will be if C is equal to 1? What is the meaning of C is equal to 1? Can you recapitulate from theory of fiber orientation? C is equal to 1 means isotropic distribution of fibers in yarn, which is of course not true. However, just for taking theoretical example, we can consider what will happen if C is equal to 1. C is equal to 1 means it is isotropic orientation. Right. C is equal to 1 means isotropic orientation. If C is equal to 1 and eta is equal to 0, then you can find it out will be equal to 3 by 8. right. This you can find it out. So, now what we would like to see is that for this theoretical example we would like to see now two curves. So, what I do here, we consider these three equations. Look specially for this equation, you know how to calculate. What we assume? We assume fiber stress strain relation is linear, and for different values of anisotropy what will happen? The moment we assume fiber stress strain relation is linear, that means this phi is now independent. So, it will be having constant value. So, we expect phi to be constant. So, look at this graph. This graph is obtained by using this function. Theta u f cos square theta u theta d theta into sin beta by cos q beta d beta and fiber stress strain relation is linear. Right. For different values of C, we obtained different values of coefficient of utilization. However, one thing is very common with Gagob's theory. The common part is that in Gagob's theory also it becomes independent of yarn strain. Here also it is independent of yarn strain. Reason is very simple. The moment you assume fiber stress strain relation is linear, it is obvious, it is going to become. But however, what we see is that coefficient of fiber stress utilization is now different for different values of C. In Gagob's theory, it is always C tends to infinity, right. Say for example, when C tends to infinity, then basically it comes Gagob's equation. So, this value gives a constant line, although it stays much higher than the other one. For different values of yarn strain, we obtain these values, they are constant, but the constant is at higher value. When the level of anisotropy changes, it reduces. So, when C is equal to 10, we again obtain it is a constant line. However, the value of constant is now little lower than it was for Gagob's model. Then for example, C is equal to 5, it is further low. C is equal to 2, it is close to 0.5, and when C is equal to 1, isotropic orientation, for different values of axial strain we obtain same value, however, this value is equal to 3 by 8. So, what we learn here with this theoretical example, we learn that the depending on the anisotropic character of fibers in yarn, the numerical value for coefficient of utilization will change. That means there is fiber orientation which is playing a dominating role in deciding fiber stress utilization in yarn, because you see this value say for 3 by 8 and from 3 by 8 to here it is very close to say 0.9, we obtain these values. Now, in this if you carefully observe, there are thick lines and thin lines. Say for a given value of C, we always observe one thin line, one thick line. What are they? The thick line and thin line, the thick line is assumed contraction ratio is equal to 0 and the thin line contraction ratio is 0.5. That means, say this line contraction ratio is 0 and this line contraction ratio is 0.5. Right. This information was already known from Gegoff's theory. Not Gegoff's theory, but the modification of Gegoff's theory where the influence of contraction ratio was considered. However, what the new information we obtained from here is that depending on the level of anisotropy in fiber orientation, the coefficient of tensile stress utilization or force utilization will be different. Right. I wish to repeat once again that C is equal to 1 is not true practically for yarn, because C is equal to 1 is related to the isotropic fiber orientation, which naturally occurring twisted yarn not true, because twist does not give them isotropic distribution. So, practically C is equal to 1 is not valid for yarn. However, higher than C is equal to 1 is probably valid for yarn. Now, we would like to study again these functions, the last one as a function of beta d, how it will look like. So, this is the result. Behavior of utilization beta d for partial generalization of helical model. As I told you earlier, C tends to infinity corresponds to Gegoff's equation. So, here the first one corresponds to the Gegoff's theory. Here also you see for each value of C two curves, one is thin, one is thick. The thick one eta is equal to 0, thin one eta is equal to 0.5. So, this corresponds to Gegoff's theory. So, as the value of beta d increasing, the utilization is decreasing. Same trend, same observation, higher is the twisting, lower is the utilization. That means, a highly twisted yarn is mechanically weaker than a low twisted yarn because of fiber obliquity. When the value of C is lower than infinity, so the level of anisotropy is less in the yarn, then what will happen? Then the curve will follow, when eta is equal to 0, the curve will follow this, and when eta is 0.5, the curve will follow this. When C is further low, C is equal to 5, the coefficient of utilization is low, further lower. When C is equal to 2, non-linearity is also reducing. When C is equal to 1, it becomes completely linear and the value is 3/8. However, C is equal to 1 is not true in case of naturally occurring twisted yarn. What we see here is that as the level of anisotropy in yarn is reducing, that means from C tends to infinity to C tends to 1, the coefficient of fiber stress utilization in yarn is also decreasing. So, the fiber orientation distribution plays a very important role in deciding the coefficient of utilization of fiber stress in yarn. This was not considered in Gegoff's theory, right. So, what we overall observe is that the effect of yarn structure is very significant in deciding the fiber stress utilization in yarn. So far in this module, we talked about a generalized theory according to helical model. Then we modified the helical model, we tried to partially generalize the helical model and we developed equations. Those equations, their behavior we discussed. Today we will stop here. In the next class will be very interesting and also important, because in the next class we will compare experimental results, Gegoff theory, generalized form according to helical model and partial generalization of helical model. All these theories will be compared with experimental results, and we would like to see how these theoretical relations stand in front of experimental results. This we will do in the next class. Thank you for your attention.